Okay, so let's draw the dot structure for carbon tetrachloride. First thing we want to do is count up the total valence electrons. Our carbon has 4 valence electrons because it's in group 4. Then we have chlorine, which has 7, and we have a total of 4 chlorines. So that gives us 28 plus 4 gives us 32 valence electrons that we have to place. So the first thing we want to do is determine our central atom after we've determined our total valence. Our carbon is the least electronegative, so we put our carbon and we attach it with a single bond to each of our chlorine atoms. Each bond is 2 electrons, so we place 2, 4, 6, 8. So I can subtract 8 electrons from my total, and that gives me 24 electrons remaining. I now place them 2 at a time around my terminal atoms until each one has an octet. So 2, 4, 6, and the bond counts as 2, so that's 8. This chlorine, 2, 4, 6, 8. 2, 4, 6, and the bond is 8. 2, 4, 6, and the bond is 8. So we've placed an additional 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've placed another 24 electrons, so we have no valence electrons remaining. So we don't need to put any electrons around our central atom. So the last thing we need to do is check to see if our central atom has at least an octet. We know the terminal atoms do. Our central atom has 2, 4, 6, 8, and so it has an octet. So this would be the correct electron dot structure for carbon tetrachloride. Okay, now let's take a look at the dot structure for H2O, water. First step, we count up our total valence. Hydrogen has 1, and we have 2 hydrogens. And then we have 1 oxygen. It's in group 6, so it has 6 valence. So that gives us a total of 8 valence electrons that we have to account for. We next determine our central atom. Hydrogen is the least electronegative, but hydrogen can never be our central atom. So it must be oxygen. So we put oxygen and then put a single bond between the oxygen and each of our hydrogens. That gives us 2 4 electrons that we've placed. So we have a total of 4 electrons remaining. Now, hydrogen, even though it's the terminal atom, we cannot put any lone pairs around hydrogen. We can never put lone pairs around hydrogen. It has only a 1s orbital, so it can only hold 2 electrons, which are right here. So the remaining 4 electrons go around our oxygen in pairs, like this. So here we've placed the last 4 electrons, so we have no electrons remaining. So let's check to see if we need to make any double bonds. Our hydrogens are fine, and our oxygen has 2, 4, 6, 8 electrons. So this is the correct electron dot structure for our water. Next molecule that we want to draw the dot structure for is the hydronium ion. First step, we count up our total valence. Hydrogen has 1, and we have 3 hydrogens. We have 1 oxygen. That's in group 6, so it has 6 valence. And this molecule has a positive 1 charge. So that means it's deficient in electrons, so we subtract 1 electron from the total. That gives us a total of 3, 9, minus 1, 8 valence electrons that we have to place. So now we determine our central atom. Again, hydrogen can never be your central atom. So oxygen will be our central atom. We draw it bonded to our terminal atoms, which would be hydrogen. We've placed 2, 4, 6 electrons at this point, and so we have 2 electrons remaining. The remaining electrons cannot go around hydrogen, so they must go around our central atom, which would be the oxygen. So there we've placed our last 2 electrons, which means we have 0 remaining. And so this would be the final structure. Now this is a molecular ion, a cation, and so we like to put brackets and put the charge outside. The next molecule that we're going to draw the structure for is CH2O. This is called formaldehyde. First step, we count up our total valence. Carbon is in group 4. We have 1 of those. Hydrogen is in group 1, and we have 2 hydrogens. And we have 1 oxygen, which has 6 valence electrons. So formaldehyde would have a total of 12 valence electrons that we have to place. So our least electronegative atom is our central atom. Again, hydrogen can never be your central atom, so that's going to be our carbon. We draw the central atom bonded to our terminal atoms, and now we've placed 2, 4, 6 electrons, and so we have 6 electrons remaining. We put those around our terminal atoms, again never around hydrogen, so I'm going to put them 2, 4, 6 around my oxygen. The oxygen now has an octet, 2, 4, 6, 8. We've placed our additional 6 electrons, so we have no electrons remaining. So now we just check to see, does our central atom have at least an octet? Carbon has 2, 4, 6. It does not have an octet, so we need to make a multiple bond. We're going to take a lone pair from our oxygen, and it doesn't matter which lone pair you choose, and we're going to convert that lone pair into a bonding pair. Now we check again. Our carbon has 2, 4, 6, 8 electrons, so it has an octet, and the oxygen still has 2, 4, 6, 8, so it has an octet. So this would be the correct dot structure for formaldehyde. Now, I just want to note, it doesn't matter where you put the oxygen, if you put the oxygen up here or over here and the hydrogens on the top or bottom, it doesn't matter where you put those atoms. Now we want to draw the dot structure for sulfur hexafluoride. Count up our total valence, and sulfur is in group 6. Fluorine is in group 7, and we have a total of 6 of those, so 7 times 6. So our total valence electrons are going to be 48. That's an E. So we put our least electronegative atom as our central atom. That's going to be the sulfur. And we draw it bonded to our terminal atoms, our fluorines. Okay, so we've placed 1, 2, 3, 4, 5, 6 fluorines. We'd like to try to spread them out as much as we can. So we have 1 sulfur, 1, 2, 3, 4, 5, 6 fluorines. And we've placed a total of 2, 4, 6, 8, 10, 12 electrons thus far. So we subtract those from the total. And that gives me 36 electrons remaining. Now we place those electrons 2 at a time around our terminal atoms until each one has an octet. 2, 4, 6, and the bond makes 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, and 8. So we've placed an additional 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. We've placed an additional 36 electrons. So we have no more valence electrons to place. Each of our fluorines has an octet. Now we need to check to see if our central atom has at least an octet. Our central atom has 2, 4, 6, 8, 10, 12. So sulfur has more than an octet. Now that's okay for sulfur because sulfur is in period 3 or greater. And so our rule tells us that those guys can have more than an octet because they have d orbitals, which can hold some extra electrons. So we have at least an octet with sulfur. So this is a correct dot structure for sulfur hexafluoride. Next, we want to draw the dot structure for iodine trichloride. We count up our total valence. We have one iodine, it's in group 7. Chlorine is also in group 7. We have 3 of those, so that gives us a total of 28 valence electrons that we have to place. Our iodine is the least electronegative, so we're going to put that as my central atom. I'm going to draw single bonds between the iodine and each of my chlorines, and I've placed 2, 4, 6 electrons thus far, and so I have 22 valence electrons remaining. We have to put them around our terminal atoms 2 at a time, 2, 4, 6, 8, until each one has an octet. 2, 4, 6, 8, 2, 4, 6, 8. So each of our chlorines has an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we've placed an additional 18 electrons. That means that we have 4 electrons remaining that we have to place. Our rule tells us that we put them around the central atom. So we don't want to make any double bonds yet. We put the remaining electrons in pairs around our central atom. It doesn't really matter where you put them. We just don't want to put them in between the atom and a bond, but right up here is fine. So we've placed our remaining 4 electrons, so we have none remaining. Let's check to see if our central atom has at least an octet, has 2, 4, 6, 8, 10. Again, iodine here has more than an octet, but that's okay because iodine is in period 3 or greater, so it can hold more than an octet. So this would be a correct dot structure for iodine trichloride. And now we want to draw the dot structure for C2H4. This molecule is called ethene. We count up our total valence. Carbon is in group 4, and we have 2 carbons. And hydrogen is in group 1, and we have 4 hydrogens. So that gives us a total of 12 electrons. Now this molecule is going to be a little different. It actually has 2 central atoms. So how do you know that? Well, we can play around with it and try to draw dot structures. Let's say that we connect everything to one of our carbons, our central atom. We put carbon with the other carbon, and then we put all 4 hydrogens around our central atom. Okay. So we have the carbon attached to another carbon and 4 hydrogens. We place 2, 4, 6, 8, 10. And so we have 2 more to place. We would place those around one of our carbons here. If we look at this, this would not be a correct dot structure. Our carbon here has less than an octet. This carbon has more than an octet. Carbon is in period 2, so it cannot have more than an octet. So this would not be a correct dot structure. So the only way to make this into a correct dot structure is to draw it kind of like this, where you have the carbons bonded to each other, and then we have one hydrogen here, and then the other hydrogens be over here on the other carbon. So here we place 2, 4, 6, 8, 10 electrons, and we have 2 electrons remaining. We put those around either carbon, it doesn't matter which one. Of course, they can't go around the hydrogen. And now we check, do each of the carbons have at least an octet? This carbon has 2, 4, 6, 8. This carbon's good. This carbon has 2, 4, 6. So this carbon does not have an octet. So our rule tells us if one of our central atoms does not have an octet, that we need to take a lone pair and convert it into a bonding pair. Now, this carbon has 2, 4, 6, 8, and this carbon has 2, 4, 6, 8. So both carbons have an octet, and so this would be the correct structure. We've placed all of our electrons. So this would be the correct structure for our ethene molecule.